Greetings and welcome to this virtual tour of the largest rooftop solar photovoltaic system in the state of Wisconsin. My name is Ken Walls and I'm a science and engineering instructor here at Madison Area Technical College in Madison, Wisconsin. And I'm the director for the Center for Renewable Energy Advanced Technological Education. And I'll be your tour guide today. Before we begin, I should note that this work is partially funded by the National Science Foundation, although the views, opinions, and recommendations contained are those of Madison College and the Create Energy Center and do not necessarily reflect those of the National Science Foundation. We are under a COVID-19 coronavirus lockdown, so it's likely that we'll see few, if any, students on the tour today. And I hope you'll be able to hear okay once we get indoors, because I will be speaking through a mask. I should also note that this is not a professional video production. There is no camera person, no sound crew, no teleprompter, no makeup artist, and it's been a long time since I've been to a barber. So please forgive the somewhat amateur quality of this presentation. So with that said, let's take a walk inside and see if we can get up on the roof. We are inside the building, so let's take a quick look around. We are standing in the new Truax Gateway edition that was built with a referendum about 5 years ago. We can see it's a three-story structure with a lot of daylighting. The design for this new expansion of the campus was originally conceived through a student design project in our architecture program. One of the elements of that design was to have a three-story waterfall. For energy efficiency reasons, that wasn't constructed, but you can see we built this sort of virtual LED simulated waterfall instead to kind of honor the students' design ideas. We're going to continue taking a walk upstairs, up a flight of stairs to the third floor to gain access to the roof. Madison College installed its first solar PV system in 2002, and a picture of it is shown here. This was a 1.2 kilowatt system. By comparison, the new system that the college commissioned last year is 1,850 kilowatts. The original system was composed of 20 Kyocera 60-watt modules that are shown above. And the new system is composed of over 5,700 Yingli 325-watt modules, which are shown below for comparison. You can see that the new modules are considerably larger, with a surface area about 3.5 times as great and a rated power more than 5 times that of the older system. This is illustrative of the transformation in the solar industry that's happened over the course of the last 20 years. It should also be noted that the original system had an installed cost of about $18 per watt. The college's new system was built for under $1.70 per watt, so there's been more than a 90% reduction in cost during this same time period. This is a flyover photo of the new solar photovoltaic system commissioned at Madison College in 2019. The system contains 5,700 solar modules, each of which is rated for 325 watts. The total system size is 1,850 kilowatts, or 1.85 megawatts, making it the largest rooftop solar system in the state of Wisconsin. When skies are clear, the system creates enough electricity to power the 1.1 million square foot facility for several hours over the middle of the day. Of course, many days in Wisconsin are overcast, and the school also teaches classes at night, so over the course of the year, this provides about 25% of the building's energy. This is roughly equivalent to the annual energy consumed by about 300 residential homes. Well, here we are up on the roof and standing outdoors, which means I can now speak to you again without wearing a mask. Behind me, you see a portion of the solar array here at the college. I should mention that when we originally conceived this project, it was part of an entire solar roadmap plan that the school put together. We looked at all of our locations and all of our facilities and then tried to prioritize which of those projects would be the most beneficial to the school. In developing the plan, the school ranked our priorities for why we would pursue solar, and the top two motivations turned out to be economics and educational benefits. So this campus, the Truax campus, is the largest campus that we operate. It serves the biggest number of students. It's also the largest electrical consumer. Our bill here is over $1 million a year for electricity. So by pursuing solar at this location, we could meet both of those two motivations and sort of get the biggest bang for the buck, so to speak. So here we see another nice view of the system. As you can see, the majority of the system installed here at Truax is south-facing panels on what are called ballasted racking system. If we take a little bit closer look at this racking system, the important thing here is that there are no roof penetrations with the racking system. All of the panels are simply held in place on these plastic trays with the concrete blocks sitting on a slip pad on the membrane roof. And it is simply the force of friction that keeps these panels in place and prevents them of moving around in the event of a storm. There's obviously some wind load calculations that go into that. For those of you that have taken a statics course, there's some nice calculations for future engineers to determine how much of the ballast rock needs to be placed and exactly where it needs to go in the layout of the array. When designing this solar system, we also wanted to take advantage of different elements of the building to provide educational benefits for students that are in our renewable energy program, learning to design, analyze, and model the performance of solar photovoltaic systems. Here we can see two adjacent roof sections on the building. One on the left with the panels installed on a black EPDM rubber roof, and the other on the right with the panels installed on a white TPO polymer membrane roof. The reason this is important is because those two solar arrays will experience different thermal environments due to the absorption of light by those two different roof surfaces. The temperature affects the electric potential of the solar panels, or the voltage of the panels. As the temperature increases, the voltage decreases. So we will see differences in performance between these two roof surfaces, and our students can gather and analyze that data to see how those characteristics impact the annual energy production from these two arrays. Here we see another type of roof surface for the system at Madison College. You're looking at the standing seam metal roof on the south-facing facade of the building. The panels in this case are attached directly to the seams on that metal roof, and this provides yet another type of thermal environment for the operation of those panels. We'll take a little bit closer look at the mounting structure there so that you can get a better, more detailed view. So let's take a closer look at these panels mounted on the standing seam metal roof. I will walk up here and try and zoom in so you can get a look at how these panels are attached to the standing seams on the roof. There's an end clamp here that attaches directly onto the seam with a couple of hex head bolts there, and then an end clamp that affixes the panel onto the roof surface. You can see that there's a small gap between the panel and the roof itself to allow air to flow behind the panel, and that's so that the panels have some sort of convective cooling to try and control the temperature. Again, as we know, as temperature increases, the voltage drops. I think we can hear a fire engine in the background there, so I'm going to stop recording for a little bit and resume once the emergency responders are gone. When designing the system for Madison College, we knew that we had two goals. The first being to generate energy for the building, and the second being to use the system to educate our students in our renewable energy program. Oftentimes when designing a rooftop solar system, it's difficult to provide access to students due to safety concerns of being on a roof. Furthermore, at our school, the only access to the roof was up a steep vertical ladder and through a ship's hatch, which rendered the roof inaccessible for use as instructional space because it wasn't accessible for students. Our solution was to knock out a wall, as you see here, install a new exterior door opening onto the roof, and this ADA accessible ramp to provide a way for students to get access to the roof. We also use this space to provide an interpretive display and a viewing observation deck of the system that we'll take a look at here. So even in inclement weather, students can come and use this space. They can see some of the solar panels and the inverters out here on this lower roof elevation section. And then you can see up above here we have some interpretive signage about the system, and we'll take a closer look at that in just a sec. Here you're looking at the smallest array that makes up the system at Madison College. This is about 20 kilowatts, or 1% of the total panels installed at the school. But more importantly, what you're seeing here is the student instructional array. So you can see this roof section is at a lower elevation from the surrounding parts of the building, which makes it virtually impossible for a student to fall off the roof. And it also was in such a spot that we could isolate it from the rest of the array to allow students to work on this part of the system. The devices you see on this wall are DC to AC inverters. So solar panels all produce DC power. Of course, our building operates on AC, alternating current. So we need to convert that DC power into AC power, and that's what these devices do. Each one of the white units that you see is a 33 kilowatt AC inverter. And if you're looking on the right side next to the gray cabinet there, you can see that there are 3 of those inverters that are wired together into a single disconnect switch that sits just below them here. So we've got 1, 2, 3, 4, 5, 6 disconnect switches. Each of those units is 33 kilowatts, so 33.3 actually, so times 3, that's about 100 kilowatts right there. Another 100, another 100. Here's 66, 66, and 66. So if you add all that up, you're looking at roughly about 500 kilowatts worth of inverters there. This is about a third of the total system output. There are 2 other banks of inverters like this on other sections around the roof. As you're looking at this picture, you probably notice that the inverter over here on the left looks different than all the others. Let's take a little bit closer look at that one. We can see that it's considerably smaller. This is the inverter for the student instructional array. And it was installed intentionally for the students to be able to disconnect this part of the system from the rest of the larger photovoltaic system that serves the buildings. Here we can see a close-up view of that small inverter for the student instructional array. If we look at the disconnect here, you can see that by turning this knob, they can switch this over to the off position. That de-energizes the student array, and then we can apply a lock and a tag to this. We teach lock and tag out procedures for safe electrical work. And then the students can disassemble, take apart and inspect this system, and then reinstall it, all while the rest of the system continues to produce power for the building. So just a couple other considerations that went into the design of the student instructional space. We can see a few things here. We've got the guardrails there to prevent folks from walking over by the skylights, and also to discourage any mischievous students from rapping on the windows of the people with offices in the background there. We also see down below here these gray walkway treads, and you can see a large area of gray tread installed all around the perimeter of the array here. You wouldn't normally have this much of that traction tread installed, but we wanted this space to be able to accommodate large groups for public tours. So it was something we requested of our roofing contractor. I should note the TPO white polymer membrane roofs are incredibly slippery if they get wet. So having some sort of a traction surface like this is pretty much mandatory if you're going to have people out on the roof, either working as part of a class or out there touring as part of a public outreach group. One of the other questions we're oftentimes asked is about the weight load on the roof itself, and if we're adding a bunch of these ballast bricks here to hold the system in place, don't we have to be concerned about the structure underneath of the roof? And that is certainly true, and it is a calculation that any solar contractor would need to do for a building. In our case here at Madison College, it wasn't a large concern for our building. Our building has about a 6-inch concrete roof, steel reinforced, that is below us. The building was, when it was originally built, was engineered and designed to actually be able to accommodate an additional story addition on top of it if the college ever grew large enough that it needed to add that space. I'm not a civil engineer, but what I am told is that the soil mechanics actually are not strong enough to support an additional story up above. But the building is certainly well engineered enough to hold the weight load that is represented by our solar system in these concrete blocks. Another question we often get is what happens if there is shade or shadows obscuring the panels. Right now we've got some cloud cover overhead, and that's reducing the amount of sunlight striking the panel surface, and as a result the electrical output is correspondingly reduced. The majority of our system experiences no shade at all. We're a 3-story building, and the building is taller than any trees around us, so there are no structures available to provide shade. The one exception here is this portion of the student array, which is on the lower elevation section of the roof. Right now we're looking to the west, and you can see the wall for the higher roof elevation in the background there. In the late afternoon hours, that wall will cast a shadow on the edge of the panels nearest to that roof. We actually could have avoided that if we had changed the layout of this array somewhat, but we intentionally placed them the way we did because we train students in our program to be able to do shading analysis and to model the impact of what that shade will be on the electric output of a system. This slide shows the data monitoring dashboard for the solar system at Madison College. This information is displayed on a flat screen kiosk near the observation deck for the system, and is also accessible online remotely. So even during the coronavirus lockdown, our students can access data. We see production data here for the final week of May and first few days of June. You can see on June 3rd we had a nearly cloud-free day and almost entirely clear skies and solar performance throughout the day. The system also provides some information about the lifetime revenue and energy generated, as well as environmental benefits for the system. It's kind of remarkable to note that although the system's only been operating for a year, it's already offset over 1 billion kilograms of carbon dioxide emissions, which has the roughly equivalent environmental benefit of having planted nearly 70,000 trees. So one way to sort of think about the benefits of this system is it's sort of akin to having created a school forest. The solar system has a pretty sophisticated data gathering and archiving system. The modules have DC power optimizers on the backs of each module that allow the modules to operate independently of one another within a series string. There's one optimizer that serves every 2 modules, and the optimizers also have an independent communications signal that transmits data up to the cloud about the performance of that optimizer and its modules. The system can be accessed remotely. Students can then export this data as a comma-separated values file for analysis. You can see here that the system can be selected down to individual subarrays or individual strings. In the case of the green box that you see there, we're kind of looking at the student instructional array. So this can be used for doing experiments. For example, students could implement an experiment where they clean one of the strings of panels on a regular basis, say every month, while they leave the other string, whether in place naturally, to find the potential benefit of having a maintenance schedule for preventing soiling of solar panels. This is just one example of the many types of experiments that might be done with a system like this. Common question we get is how long will the solar panels last? So the simple answer to that is that the panels have a 30-year warranty. But I need to explain that just because the warranty is 30 years, that doesn't mean that after 30 years they cease to work. The way the warranties for solar panels are designed is usually based on a percentage of their rated production capacity. So these panels are rated at 30 years to still produce 85% of their rated power output. They could continue to function for far more than 30 years, and there's solar panels in the field that have now been operating for 40 to 50 years. Keep in mind that the simple payback period for the system was 10 years, so you can imagine if 30 years from now these panels are still producing power, the school will have come out pretty well on its financial investment. Well, this concludes our tour of the largest rooftop solar system in the state of Wisconsin. On behalf of Madison College, thank you for joining us. Before we part ways, I'll mention a few resources that are available if you are considering pursuing solar at your school. The college has authored a paper with the American Society for Engineering Education that examines various design aspects of engineering a system for a school facility. We have also authored a how-to guide, a 10-step how-to guide for creating a solar roadmap that will be of interest if your school is seeking to incorporate solar into its strategic plan. We also have a model request for proposals for schools that are seeking to contract with solar developers. These resources and many others are available in a new solar toolkit that is available on the Create Energy Center's website, which is www.createenergy.org. Lastly, I just extend a personal invitation to anyone viewing this video. Once the virus is over and things are back to normal and the school is open for business, I'd encourage you to pay us a visit here in Madison, Wisconsin, and I'll be happy to give you a personal tour and get you up on the roof so that you can see the system up close. Thanks again for joining us today, and I wish you all good luck in your own solar endeavors.